This video looks at the impact of adding a t-filter into GPC. The previous video demonstrated how to use the use of filtering before prediction gives rise to different prediction equations. And here's an example of what we showed. We showed if you use this filtering trick, you basically got p tilde delta u tilde past instead of p delta u past, and q tilde y tilde past instead of q y past. This video looks at the impact of incorporating these new predictions into GPC. How does the control law change, and how do the poles, sensitivity and performance change? First then, let's start with the basics of GPC, which is we're optimizing a performance index J subject to some predictions. So what happens when we include a t-filter? Well, you'll notice the performance index is changed very slightly just because we put in these new predictions, and the control law will come out like this. You'll notice the only real change is I've got this p tilde delta u tilde past, q tilde y tilde past in the control law. Now you might want to compare how this was with the original GPC law, and unsurprisingly you'll notice the difference was these terms here. But it seems to be quite a subtle difference otherwise. Now, the GPC control law is summarized like this now that we've used these t-filter and we've used these filtered variables. So how is that going to affect our transfer function representation of the law? What I'm going to do is unpack each of these terms in more detail. So if you take the first term, delta uk, again as in the earlier videos, you can show I can express this as PR rk plus 1, that's not changed. I've got this PR p tilde, where PR is given by this term here, and p tilde we know, and you can then basically write that PR p tilde equals this dk check tilde term, and PRQ tilde is this NK tilde term. So this is conceptually the same as the early videos, which is why I'm doing it very quickly. What we want to do next is convert this expression at the bottom to Z transforms, because by converting it to Z transforms we can actually start to compute the sensitivity functions. So a GPC control law can be summarized like this, and you'll notice exactly as we did before, we unpacked each of these vectors to say what terms are in there. So the pre-filter is not going to come into it, but P1 to Pn, and then this denominator term D1 to DNB minus 1, and numerator term N1 to NNA, multiplying past filtered variables. And we said you could rewrite these using difference equations. So basically, instead of writing delta U tilde past, I can now just write delta U tilde k, and you'll see I've got all these z to the minus 1, z to the minus 2, and so on. So it's an equivalent representation. So I'm not going to dwell on that because we did that in the earlier video. But the key thing to note is I've got a delta UK here, but a delta U tilde of k here. And that's our conundrum. We've got a mix of filtered and unfiltered variables. So how are we going to get ourselves out of this? Well, as it transpires, the answer is fairly simple. Just remember that delta U tilde equals delta U over t, y tilde equals y over t. So, if my control law takes this form here, you'll see I've got delta U of z equals PR times R of z, and then this dk tilde check of z times z inverse delta U of z all over t. And you'll notice what I've done is instead of writing delta U tilde, I've written delta U over t. And similarly, where I've got this nk tilde of z, I've written y over t. So I've removed the filtered variables from the expression by substituting in from these expressions at the top. Now, what I can do is I can multiply the left-hand side by t. So in other words, I can write t delta U over t, and then I can move all the delta u's to the same size, and I get this. You see I get t plus z inverse dk check tilde all over t times delta u plus pr times r minus nk tilde of z times y over t. Now again, I've done this fairly quickly because the algebra is moderately straightforward. Let's look at the new block diagram then. So you'll notice the control law has changed slightly, because now multiplying delta u we've got this dk tilde over t, and multiplying y we've got nk tilde over t. So in other words, my control law now takes this form, nk tilde over t there, t over dk delta here. I'm just assuming CZO. You can worry about the complexities for MIMO. It's conceptually the same. So you'll notice the block diagram is subtly different from what we got when we didn't have a T filter, because the T filter has come into the expression here, and the T filter has come into the expression here, and I've forgotten my tilde, but I've got nk tilde and dk tilde instead of nk and dk. Having done that, I can of course now do all the standard sensitivity analysis. So first of all, where are the closed loop poles? Well, you can show that the controller reduces to nk tilde over dk tilde delta. The reason is you'll find that the t's will cancel. If you've got a system G equals B over A, and I say, okay, where's my closed loop pole polynomial? It's fairly straightforward to show. You get this dk tilde delta A plus B nk tilde. Now, if we were to determine the transference from target to output, you would get an expression a bit like this. You'll find you get TB over dk tilde delta A plus B nk tilde all times PR times R. So that's with a T filter. Now if you remember, without a T filter we had this expression over here, and the interesting thing is they must be the same, because if we're just saying that all the T filter does is basically give you a different mapping for noise or disturbances, if there was no noise and no disturbances, you must get identical mappings, because you're minimizing the same performance index with the same degrees of freedom. So in other words, these two expressions here have to be identical, but you're looking at them saying, well, they don't look the same to me, so let's see what we can do. We've not changed the performance index, we've not changed the degrees of freedom or the flexibility in the predictions, and therefore in the absence of uncertainty, both control laws must give identical solutions. So nominal tracking, which is response to changes in target, must be identical, and therefore you get this, that TB over dk tilde delta A plus B nk tilde must be the same as B over dk delta A plus B nk. And what does that tell you? It tells you this, that dk tilde delta A plus B nk tilde must be the same as dk delta A plus B nk all times T. Very simple relationship between the coefficients of the compensator with the T filter and the coefficients of the compensator without a T filter. Now that observation can be quite useful, because if now I try and calculate all my sensitivity functions, and for PC I'm going to use PC equals A delta dk plus B nk, so I've got the same PC throughout, then if you take my block diagrams and substitute everything in, what you'll notice is the sensitivity functions with the T filter all include this extra T in the denominator. So okay, the numerator is slightly different. This one had nk, this one has nk tilde, this one has dk, this has dk tilde, this one has nk, this has nk tilde, but the most important difference is that this T appears explicitly in all the denominators. So the low-pass filtering appears to have an impact on all the sensitivity functions. You said 1 over T is a low-pass filter, and 1 over T has affected all your sensitivity functions. So therefore, some low-pass effect has occurred on your sensitivity functions as desired. So the T filter does change loop sensitivity, but not nominal behavioural poles. However, the actual impact is quite difficult to discern in advance, because although the sensitivity functions all include T in the denominator, there are also non-simple changes to the controller parameters. So you'll notice dk went to dk tilde over T, nk went to nk tilde over T. So it's not quite clear-cut to say that you will get a pure filtering effect. Yes, you will get some low-pass filtering because T's in the denominator, but the impact of the change of dk to dk tilde is a bit less predictable. Experience, however, does show that the T filter helps, but, and this is really important, proposals for systematic design of a T filter in order to get any desired effect are weak at best. If you look in the literature around the early 90s, you will find there are some proposals, but you will find they're very much rules of thumb. They're not particularly rigorous. Now, as an aside, obviously in this particular video we've just assumed that you're using the same filter on every output. If you had a multivariable system, you could of course use different filters on different outputs, but I would suggest that the extra complication in algebra is probably not worth it.